Okay, so we'll continue considering how to compare means of two samples. So last day, or in the last lecture, we considered paired t-test, where individuals are paired to control for some nuisance variable prior to conducting the experiment. In this case, we're going to have two samples. The samples are often called independent samples. There is no relationship between the individuals. They're not paired in any way. We simply have a group of individuals that we might assign to control. So there could be 10 individuals acting as a control, and maybe another 10 that you've randomly determined are going to get some treatment or another. They're not paired with each other in any way. And now we're going to compare those two means. So it's called an independent sample t-test by the book. It's often also called a two-sample t-test for comparing means. Among the things we need to do, ultimately we're going to calculate a t-statistic, a test statistic. And to do that, we need to get the standard error of the difference in means. And to do that, we need to estimate something called a pooled variance. We'll compute t-calc. And then finally, there are assumptions as associated with all of these statistical tests we've conducted so far. And that is that the populations that are sampled are normally distributed. So we have two populations we imagine sampling. Those are both normally distributed. So that's one assumption. And the second assumption, perhaps a somewhat more important assumption, is that those populations also have equal variances. The true variances of the populations are equal. So those are the assumptions. And so let's just move ahead, and I'll just first write down what the test statistic is and how you obtain a pooled variance. So let's imagine we have two samples. We'll just call them sample 1 and sample 2. And so sample 1 has a sample size of n1. Sample sizes of the two groups you're comparing don't have to be equal. Of course, it's always better to have equal sample sizes. It increases the power of the test than if sample sizes are not equal, but you can still conduct it. So sample 1 might have a sample size of n1, and we will compute a mean for it called x1, and we need to get its variance because we need to use the variance in actually a couple of ways, and I'll just talk about one of them today. For sample 2, we'll get the same kind of information. So sample 2 can have a different sample size. We'll call it n2. We'll be able to calculate a mean, or estimate the mean, and we'll estimate the variance. So this is really summary statistics that we might calculate in any case. Once we get hold of some numerical data, again, this applies to numerical data, we're comparing means. And so ultimately what we want to do is to calculate a test statistic, what I've typically called like a t-calc. And in this case, the t-statistic is just going to be the difference in means. You can subtract 1 from 2 or 2 from 1. It often makes no difference, but it's helpful to know which way you're subtracting, especially if you're going to do a one-sided test. So here we go. It's the difference in means divided by the following, and this quantity I'm going to write down in here, it's really the standard error of the difference in means. So I'll write it as the standard error of subscript x bar 1 minus x bar 2. So the standard error of the difference in means. So that everything here is absolutely straightforward. It's trivial to estimate the means of the two samples and obtain the difference in means. How do you get this standard error of the difference in means? So that takes some work to get. And so to get it, the first thing we need to do is to estimate something called the pooled variance, which I'll symbolize. So pooled variance. And I'll use the symbol SP squared for pooled variance. And so it's simply n1 minus 1 times the variance that you've estimated for sample 1 plus n2 minus 1 times the variance you've estimated for sample 2, and then divide all that by n1 plus n2 minus 2. So that will give us the pooled variance. Once you have the pooled variance, you can then compute the standard error of the difference in means that we need in order to ultimately do our t calculation. So the standard error of the difference in means equals the square root of the pooled variance that we've just estimated divided by n1 plus the pooled variance divided by n2. Now I've given you this equation in a general form that will apply to equal or unequal sample sizes. If the sample sizes are equal, this simplifies in some way, but it's probably, rather than having proliferation of different equations, this single equation will suffice for equal or unequal sample sizes. So that's what I suggest you use. Other piece of information we need is the degrees of freedom. So for a 2-sample t-test, or independent sample t-test we're conducting now, the degrees of freedom are n1 plus n2 minus 2. And so we're going to need the degrees of freedom in order to refer to the theoretical distribution of t with that many degrees of freedom, because we're going to obtain a critical t value with alpha equal to 0.05. It could be 1 or 2-tailed. We'll have to adjust their reading of the t-table accordingly, and with the appropriate degrees of freedom. So that's the sort of mechanics of what we need. Finally, and I perhaps should have started with this, typically the null hypotheses are of the form that the mean of sample 1, the true mean of population 1 equals that of population 2. And the alternate hypothesis can be 1 or 2-sided depending on the experimenter's view. So this would be a formulation for a 2-sided test. And so that's basically the mechanics of a t-test, an independent sample t, where first of all we'll get some summary statistics, the sample size, the mean, the variances. We can calculate a pooled variance. We can estimate the standard error, the difference in means. We need that in order to construct the t statistic. And then we can do the t-calc and compare it to the critical value. So let's now go ahead and do a couple of examples. And so I'll describe an experiment we're going to conduct. And so it's some experimenter's idea that fertilized tobacco plants produce larger leaves than unfertilized. A very trivial, simple experiment. And embedded in the experimenter's view, and the reason they're carrying out the experiment is to try to get bigger tobacco leaves. And so they're going to have hypotheses of the following form. The null hypothesis is going to be, really it's always the same for these, that the fertilized group will equal those of the control. No difference, in other words, in the size of leaves. And this is going to be an alternate that's one-sided, because the experimenter is fertilizing them with the notion or hope that they'll get bigger leaves. So we've got a one-sided alternative hypothesis in this example. Okay, so then you conduct the experiment, and I won't give you the raw data here. Instead, because you know how to calculate means and variances, I'm just going to give you the summary statistics. So for the fertilized plants, here are the summary statistics. So the mean for fertilized equaled 20. There were 7 of those, so the sample size was 7. And the variance was estimated for that sample to be 5.83. For the control group, so an independent sample was obtained. Those plants were not given fertilizer. Their mean leaf size was 18. The number of control plants was 5, so there were unequal sample sizes. You can still conduct the test. It's just not the best, it's not the most powerful approach to take. It's better to have equal sample sizes. And the variance of the control group was, what was it? It was 6. All right, so we have the summary statistics that we need, and now we can go ahead and do the t-test. And first, remember, we need to get the pooled variance. So the equation for the pooled variance in this case is the number of fertilized minus 1 times the variance of fertilized plus the number of control plants minus 1 times the variance of the control plants, all divided by the number of fertilized plus the number of control minus 2. And so in this case, the pooled variance equals 7 minus 1 is 6 times the variance, which was 5.83, plus 4 times 6 over 7 plus 5 minus 2. And if you calculate that out, you get a pooled variance of 5.898. And I'm retaining a lot of digits here because I'm going to have to use this value and divide things out in order to construct or calculate the standard error of the difference in means. So retain more decimal places for now. One thing it's probably worth your stopping and looking, because there's a lot of calculations in here. You need to get the variances correctly, then you're going to do some more calculations. The pooled variance should lie somewhere between the variance of the two samples. So 5.898 does indeed lie somewhere between 5.83 and 6.0. If your pooled variance lies outside that range, it means you've made a mistake somewhere. So that's a useful thing to look at. Because in some respects, the pooled variance it's not exactly the mean of two variances. It's a weighted mean of two variances, weighted as a function of sample size. So make sure it falls between them, or it might be very close to 6, for example, depending on sample size. But it should not be outside of the range of the individual variances. Okay, so that's good. So we've now got the pooled variance. Now we can get the standard error of the difference in means. So the standard error of the difference in means equals the square root of the variance of the fertilized group, which was 5.83. Oops, sorry. Take that back. It equals the pooled variance, which was 5.898 divided by the sample size for fertilizer, which is 7, plus the variance of the control group, which was 5.898, the pooled variance divided by the sample size of the control group, which was 5. So it's always the pooled variance in here divided by the number of individuals in each of the two groups. You divide them out, add it up, take the square root of that mess. And if you do that, I got a standard error of the difference in means equal to 1.422. And so now we can do our t-calc. Remember, t-calc is just the difference in means divided by the standard error of the difference. So the t-test statistic, the t-calc, equals the difference in means. It's 20 minus 18 over 1.422. And so our test statistic, the calculated t-value, equals 1.406. And so now we want to ask the question, is this t-value sufficiently large, leading us to reject the null hypothesis? So to do that, we need to refer to the t-distribution. So let's do that. So for the t-distribution, we need first to know the degrees of freedom. And so here the degrees of freedom, remember, it's n1 plus n2 minus 2. So it's 7 plus 5 minus 2, so 10 degrees of freedom. And this was, remember, we set up the null hypothesis as a one-sided. So we're going to refer to the critical values of the t-distribution with alpha 1 equals 0.05, with degrees of freedom equal to 10. So we need to look that up. So you have to look up what alpha 1 equal 0.05 and read off the critical value. And if you do that, you find the value is 1.812. So let me just diagram out the t-distribution again. So we're still referring to student's t-distribution, right? It's a somewhat flattened and should be symmetrical distribution relative to the normal distribution. Here's 0, minus infinity, plus infinity. What we're doing here is really setting up rejection regions at this end of the distribution. It's a one-sided test, and because of the way I subtracted the smaller mean, or the mean of the thing thought to be smaller, the control group, from the mean of the group that was supposed to be bigger according to the alternate hypothesis. I set up a rejection region where all alpha equal 0.05 lies out here. So all 0.05 area is under this portion of the curve, and we want to know the critical value. We looked that up. It's 1.812. And so our t-calc, remember, was 1.406. So the calculated t lies over here somewhere. It doesn't fall out in this rejection region. So we don't reject the null hypothesis. We have no reason to believe fertilizer increased the leaf size. No reason to believe fertilizer increases leaf size, at least in this experiment. And so that's our final conclusion. So again, a statistical statement about not rejecting the null hypothesis because t-calc is less than the critical t-value, as you can see from the diagram, and then a final simple statement, no reason to believe there's any difference between those. Okay, let's do another one of these. So another independent sample t-test. And so this time, I'll talk about another example. In this case, mongooses were introduced to Jamaica. So they're not native there, but they were introduced. It's quite some time ago. And somebody wishes to ask the question whether, given the length of time, which hasn't been very long, has there been any modification in the, or evolution of size differences in mongoose that have been introduced to Jamaica versus where they were introduced from in India? And so the experimenter doesn't suggest that they might be smaller or larger. They're just looking for differences, whether these have diverged in size through time. And so the null hypothesis is going to be really the same as always, that the Jamaican mongooses are the same size as those from India. And the alternate in this case is two-sided, because the experimenter didn't specify or have any notion as to whether or not, which way the differences might occur. So clearly a two-sided alternative. And again, I won't give you the raw data, I'll simply give you summary statistics. So the mean size of the Jamaican mongoose was 15. The sample size for Jamaican one was 10, and the variance estimate was 5. for the Indian population sample, the mean ended up equaling 10.0. The number of individuals, for the Indian population was also 10, so equal sample sizes, which is a good thing to do because it's a more powerful test that way. And the sample variance ended up equaling 6. So again, there would have been raw data here, 10 individuals in each that were then measured. I've simply given you the estimates of some of the summary statistics that we need. So the first thing we need to do is to get the pooled variance. So the pooled variance is N1 minus 1 times the variance of the Jamaican thing, and the number of Indian minus 1 times the variance of the Indian thing, divided by N1 plus N2 minus 2. So that turns out to be 9 times 5 plus 9 times 6 over N1 plus N2 minus 2. And if you calculate that out, you get a value of 5.5. Notice here that this pooled variance falls, in this case, exactly between the sample variances of the two population groups. So Jamaican had a variance of 5, and the Indian group was 6. In this case, it's 5.5 because it's the weighted mean, but the weights are the same. In other words, the sample sizes are the same. So the pooled variance really is like the average of the two variances in this case. Okay, so now that's fine, we need the standard error of the difference in means, Jamaica minus India, and for that it's the square root of the pooled variance divided by the sample size for Jamaica, and the pooled variance, plus the pooled variance divided by the sample size for India. So sum those things, take the square root, that gives you the standard error, the difference in means, and this ends up being 1.0488, again to excruciatingly many decimal places because I'm going to use that to calculate t-calc. So t-calc is given by the difference in means, so in this case it's 15 minus 10, so from the Jamaican mean size, a mongoose, I'm subtracting the Indian. You can subtract it either way, it doesn't matter. I happen to like positive numbers, so I'll subtract it in the positive direction. And then divide by the standard error, the difference in means, 1.0488. And if you do that, you get 4.767 as the test statistic. We need to know how many degrees of freedom we're dealing with. So it's N1 plus N2 minus 2, so 10 plus 10 minus 2 is 18. Excuse me. So we need to look up in the t-statistic, right? It's the critical value. It's a two-sided test, so alpha 2 equal 0.05 with 18 degrees of freedom. And if you look that up, you find that the critical value equals 2.101. And so you might recognize immediately that our calculated t exceeds that, and so we reject the null hypothesis. Or if you diagram out the t distribution, not a bad idea, perhaps. Here's the t distribution. Here's 0, minus infinity, plus infinity. What we're doing in a two-sided test, and that's why it's called two-sided or two-tailed, we're setting up rejection regions at the upper and lower ends of the distribution. They'll both have the same areas of alpha equal. We're splitting alpha between them, so this is really 0.025 area under this portion of the tail. And the other 0.025 under there. And we're looking for the critical values. We looked those up in the tables, and it turned out to be 2.101. So this is 2.101, and this is negative 2.101. Because I subtracted the smaller thing from the bigger, we're going to be looking at it in this way, or we'll notice that our t-calc, 4.767, lies out here. So we're going to reject. If you happen to have subtracted the other way, you subtracted the Jamaican 15 centimeters or whatever it was units, from 10, the smaller Indian thing, you would have negative value. You'd have negative 4.767. It would lie out here somewhere, and you'd reject the null hypothesis also. Because it doesn't matter which way you subtract. It's really only in those cases where you're doing one-sided comparisons that it becomes, you need to think about which way you're subtracting. I would always tend to subtract a thing that's supposed to be smaller from the thing that's supposed to be bigger. Then I'll always be looking at this end. If you subtract it the other way, it doesn't matter. You just need to be aware of which way you're subtracting, which end of the distribution you're going to be looking at for a one-sided test. All right, so in this case, we reject the null hypothesis because t-calc is greater than the critical value of t. Then look at the data, look at the means, and say, indeed, Jamaican mongooses are bigger, 15, whatever the units was, versus 10 for India. And that concludes that. Okay, and so the one thing, or the things I haven't addressed, so this is a two-sample t-test, nothing is paired in the experiment. You just have a random sample of mongoose from India and another random sample from Jamaica. You measure their sizes, you compare the sizes, as we've done. One thing that you really need to address is the assumptions. And so one of the assumptions is that both samples came from a normal distribution. Both populations are normally distributed. And so you could plot separately the distribution of data from both of those and see whether it meshes with the normal distribution. In both of these examples, I've given you the sample sizes. They're really too small to see, to do that carefully, but you could easily do it for a larger sample size using proc univariate. Request to plot a histogram, and you'll get like a pictorial view of whether or not the data are normally distributed, and even a statistical test for that. The other assumption is in many ways somewhat more important, and that assumption is that the variances, the true variances from which the populations are sampled, are equal. And so we'll go on next lecture and discuss how one can test that. And so that's it for two-sample t-tests.